Hi, I'm Chris with Sanderson Test Prep, and in this video I wanted to take a look at a question that involves implicit differentiation. So let's jump right into this question. This was something sent over from a colleague looking at this calculus problem. And so it says a baseball diamond is a square with side 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he is halfway to first base? And at what rate is his distance from third base increasing at the same moment? So, first things first, I'm going to zoom in a little bit here, see if I can just kind of label part of this. But we're talking about halfway to first base and the distance from second, and then also the distance from third in parts A and B. So we're going to see how those values are going to be impacted for this triangle. So let's take a look at part A by itself. And for part A, so we're going to have halfway to first base means there's 45 feet left, still 90 feet to second. We can calculate the hypotenuse using Pythagorean theorem, and that comes out to 100.623. I'm going to zoom in just to fit that in there because it's kind of tight. 100.623 feet for the hypotenuse of that triangle. So for part A, I'm try to leave the figure there and then write out part A. So we have a squared plus b squared equals c squared is Pythagorean theorem for this right triangle. And when we derive implicitly, because we're looking at a rate, we're looking at a change in distance over time. So implicit differentiation will give us 2a times change in a over change in time, or dA dt, plus 2b dB dt equals 2c dC dt. And we can plug in the values that we know. So we know values for A, and just for our purposes here, we'll call this 45-foot distance A, and then we'll call the 90-foot distance to second base B. It doesn't really matter the order of these that you use in your calculation, but just so you know what we're referencing. So here, 2 times A would be 2 times 45. And dA dt, so we have to look at how fast this is changing. So as we run along that baseline, let's see what information the question gives us as to how much that's changing. And it says towards first base with a speed of 24 feet per second. So that's the value for dA dt. So this will be 2 times 45 times 24. For B, we'll have 2 times 90 for that second leg of the triangle. And then dB dt, in this case, as we're running towards first base, is that distance between first and second changing at all? So hopefully we look at that and say, no, it seems like that's staying the same, and it is. So dB dt, in this case, is going to be 0. And then for C, we have 2 times 100.623, because we found out the hypotenuse using Pythagorean theorem. And then dC dt is what they're asking about. That is going to be what this question wants to know. They want to know how fast that distance is changing. So luckily the 0 makes the math on this work out kind of easily. It'll cancel out that term. And if we plug in all the other values and simplify, I'll zoom in and write in our correct answer. But the rate of change for dC dt comes out to 10.73. And because it's a decreasing value, we're going 10.73 feet per second closer. So that value of dC dt you might represent as a negative because we're getting closer. So that distance is decreasing. Now let's take a look at the same scenario, and we'll look at part B, and let's see for part B how that distance from third base is increasing. And we'll label things, and if you look, you're going to notice that a lot of these labels are going to come out to be similar values, right? Because we're halfway to first. So that triangle, and I'll zoom in again here to write it out to the decimal, but that's still going to be 100.623 for that hypotenuse. So part B here is going to look eerily similar to part A. We're still going to do this part the same. And I'm actually just going to copy and paste this. So for part B, we're going to have Pythagorean theorem. And then we're going to have a squared plus b squared equals c squared. We're going to do implicit differentiation. We're going to come up with 2a dA dt plus 2b dB dt equals 2c dC dt. And then we're going to plug in our known values. And so this is going to look very similar to what we just calculated. We have 2 times 45 times. Now our change in dA dt, so here, the way that this comes up with a negative is because we're technically making a smaller in part A with that negative value. And here we would technically have a plus value. This would be increasing at a rate of 24 feet per second. So that's where we can assign our signage. But hopefully we can also appreciate that a shorthand way of doing this is to write it out numerically, and then you can figure out at the end whether you should be looking at a positive or negative based on whether you're decreasing a distance or increasing a distance. So here, we're increasing a distance, plug in all the other values that we saw in part A. So we have 2b, so it's going to be 2 times 90. dB dt is not changing, right? So here, even though we're looking at the third base line, we can see that that value over there is still going to be a consistent 90. And then that means the change is 0. And we have 2 times 100.623. And then times the rate at which that hypotenuse, or that distance between where the runner is and where third base is. So that distance here to here, we want to know how fast that hypotenuse is changing as that runner is halfway to first base. So that's our equation. The 0 term cancels out. We can multiply and divide, and we come up with, in this case, a positive 10.73 feet per second. So it's basically going to be the same thing when we are calculating the increase in distance to third from where the runner is, as it is the decrease in distance to second from where the runner is in this question. So that's parts A and B for this question about a runner halfway to first base on a baseball diamond going 24 feet per second. If you have any additional questions, please feel free to comment, and feel free to check out our other videos to learn more. Thanks for watching.